Have you ever stopped to think about what makes our world, well, turn? I mean, literally, from the wobbly wheels on a shopping cart to the giant spinning turbines in a power plant, there's this incredible, usually invisible piece of engineering doing all the hard work. Today, we're going to pull back the curtain on that unseen engine, the rolling bearing.
And you know, that quote really just nails it. The range is absolutely staggering. These little components are literally everywhere, quietly making motion possible and cutting down friction in just about every machine you can think of. They are, without a doubt, the unsung heroes of the mechanical world.
So, what's the big problem that bearings were invented to solve in the first place? It all comes down to this one constant, universal enemy: friction. Friction, you see, creates heat, it causes parts to wear out, and it wastes a ridiculous amount of energy. Engineers have been fighting this battle forever, and the rolling bearing is one of their absolute smartest weapons.
All right, so let's get rolling. First, we'll dive into the heart of the fight against friction. Then, we'll take apart a bearing to see how it actually wins that fight. After that, we're going to walk through an engineer's roadmap for picking the perfect one, from understanding the forces at play to matching the type and size, all the way to those super important final touches.
Okay, so think about it. Every single thing that rotates in a machine, a shaft, an axle, a wheel, it needs to be supported. But that support creates a huge challenge. How do you let it spin smoothly while battling that relentless drag of friction? The difference here is, well, it's everything. Trying to slide two surfaces against each other is just crazy inefficient. Picture dragging a heavy box across the floor. Now, what if you put that same box on wheels? That's the magic right there. You've just converted sliding friction to rolling friction. It's so much more energy efficient, and that one principle is the heart and soul of how a bearing works.
So now that we know the basic idea, let's see how it's actually put into practice. We're going to break down the anatomy of a typical rolling bearing and see how all the little pieces work together to pull off this magic trick. A standard bearing has 4 main parts, and you're looking at them right here. You've got the outer and inner rings. Think of them as the smooth tracks, or raceways. Sandwiched between them are the rolling elements, the actual balls or rollers that do all the work. Then there's the cage, which is like a traffic cop, keeping all those elements perfectly spaced out. And finally, you've got seals, which act as bodyguards to keep dirt out and lubricant in.
And this gets to the fundamental difference between the two main families of bearings. Ball bearings, on the left, make a tiny point contact with the track. This creates almost no friction, which makes them perfect for really high-speed stuff. Rollers, though, they make line contact. This spreads the load out over a much bigger area, which means they can handle way, way heavier forces.
So with all these different options, how on earth does an engineer choose the right one? Well, it's definitely not a guess. It's a very structured process, all designed to get the best performance and reliability for the lowest possible cost.
And here it is, the official roadmap from an industry leader, SKF. As you can see, this is a serious step-by-step process. You start by analyzing what you need the machine to do. Then you move to picking the type and size, figuring out lubrication, and locking in all the final details. It really is a science. And for our explainer, we're going to focus on those first few absolutely critical steps.
Okay, this is step 1, and honestly, it's the most important one. You have to understand the forces in your machine. Where is the load coming from? How big is it? And which direction is it pushing? Getting this right determines everything else that follows.
This is a fantastic look at how a bearing handles a load. See? When a force pushes down on that inner ring, it's not just one little ball or roller that takes all the pressure. No way. The load gets spread out across several of them in what we call a load zone, which is usually around 150 degrees. This sharing of the load is the secret to a bearing's strength.
Now, the direction of that force is just as important as how big it is. A radial load pushes on the side of the bearing. Think of the weight of a car on its axle. An axial load, sometimes called a thrust load, pushes along the length of the shaft, like the force from a propeller pushing a boat forward. But in the real world, most machines have to deal with a combined load, which is a mix of both. So once you understand the forces and the environment the bearing will live in, you can start narrowing down your choices. This step is all about playing matchmaker, pairing the specific skills of a bearing type to the job it needs to do. And you can see the trade-offs right here in this chart. Need something that can spin incredibly fast? A deep groove ball bearing is a fantastic choice. But if you've got a massive radial load to support, a cylindrical roller bearing is the heavy hitter you're looking for.
And for those tricky applications with both radial and axial loads, you might look at an angular contact or a spherical roller bearing. Each one is a specialized tool for a very specific job. After you've picked the type of bearing, you have to get the right size. And it's not just about what physically fits in the space. Sizing is actually a calculation to figure out the bearing's rating life. You're basically making sure it's tough enough to handle all the expected forces for its entire planned lifespan without failing early. But the job isn't done yet. Picking the right type and size is critical, for sure, but getting these last details wrong can ruin all of that careful work. These final touches are absolutely essential if you want a reliable machine. You've got to have proper lubrication. That's the grease or oil that handles that last little bit of friction and carries away heat. You need good sealing to keep that lubricant clean and in place where it belongs. And the fit is everything. Mounting the bearing onto the shaft and into its housing with the perfect amount of tightness is crucial for it to work the way it was designed. So the next time you see something moving, whether it's big or small, remember that unseen engine whirring away inside. Picking the right bearing is this fascinating blend of physics, material science, and pure engineering precision. It's what gives us motion that's smooth, efficient, and reliable. And really, it's what makes our entire modern world turn.